Hi there, everybody. In this section, we're going to keep going with Chapter 2, and we're going to look at what happens when we have two quantitative variables. You're going to need your calculator today. And we're going to talk about the first half of this, which is scatterplots and correlation. So let's jump right in. All right, so what is a scatterplot? We're just going to start with a little descriptive thing here about what a scatterplot is. So if we have two quantitative variables, the way to visualize that is with this kind of graph. So it's very different than the sorts of graphs we've seen before. And the idea here is that there's an x-axis and a y-axis, and they're scaled appropriately to fit whatever the variable happens to be. And then what's interesting about scatterplots is that they always show you all of the information. So every dot on the scatterplot shows you every piece of data. Whereas what we saw before, even the first graph we saw in section 2.2, which was a dot plot, still doesn't show every little piece of information, whereas a scatterplot always will. So scatterplots are very detailed, which means that it's harder to discuss trends and general overview of scatterplots. So that's basically what we're going to do today. There's really only two topics in this lesson, and how to describe a scatterplot, and then other descriptive factors. So the scatterplot we just saw has to do with honeybees dancing around when they find food. It's called a waggle dance. And this is data from an experiment done on 7 honeybee scouts. And the idea is that when the food is farther away, the honeybee scouts dance for a longer period of time. So what they do is the scouts point in the direction of the food, and then they just dance. And the other bees can pick up on qualities of the dance, like how long they're dancing and the intensity of the dance. And that tells them where to fly to find the food. And then other honeybees go out and gather the food. So here we have a table of data. So here's the data. So each case, there's 7 cases, there's 7 honeybee scouts. Each case is a row. So for the first honeybee scout, the dance time was 0.4 seconds. The food was 200 meters away. And so on and so forth. For the last honeybee scout here, the dance time was 4.1 seconds. The food was basically 2 miles away. And so I'm going to go back one slide and show you what the graph looks like. That's what this scatter plot was. So you can see each case, so each honeybee scout appears as a single dot, and the coordinates of the dot tell you the x and y coordinates, or the way we do that is this is the explanatory variable in the first column, and the response variables in the second column. So we're using the time to explain the distance. So why is the honeybee scout dancing for 4.1 seconds? Because the food is a certain distance away, right? It's the scout is telling the other bees where to go. So here's your first honeybee scout, second, third, fourth, fifth, and then here's the last one, right? Dances for 4.1 seconds, and the food is over 4,000 meters away. And the idea then is we want to describe the relationship between the two variables. We want to know, is there an association? That's the first question. But because scatterplots are so detailed, we wish to learn more about the association. And that comes up with the types of descriptions we use. So there's 4 things we're going to look for. Linear versus nonlinear. Do the points form a clear straight line trend or some other curve or pattern? This is all descriptive. None of this is quantitative. Positive versus negative. If there is a trend, is it generally upward or generally downward as we look from left to right? Strong versus weak. Are the points on the graph clustered close together along the trend? And of course, we're going to look for outliers, right? But outliers and scatterplots mean something different, and we'll get there in a sec. All right, so let's talk about what all this stuff means. And we're going to start with linear versus nonlinear. So our honeybee scouts are here. This was a linear association. It's more or less a clear straight line trend. So even though the points wiggle around a little bit, that's okay. It's generally straight. That's called a linear association. And the only things we're going to do in any sort of detail in this class have to do with linear associations. There's other kinds of associations. They're much harder to do. So we're interested in, is the data linear? And then here we have something that's called nonlinear. Now there's many kinds of nonlinear associations. This is like an upside down U shape here, right? So this tells us nonlinear. So we are going to be able to analyze things like this, but we're really not going to be able to do much with this. So we just want to decide, is it linear or not? Now there's other kinds of nonlinear associations. So this was nonlinear, but sometimes if there's no association at all, that is also classified as nonlinear. It just means there's no straight line pattern. So here, this is a very random looking graph. And here, this is a horizontal line. And it turns out that horizontal lines are also considered to be no association. So it's linear, but it's no association. So there's kind of a lot going on here because these graphs are so detailed. Again, go back and look at this, right? Linear versus nonlinear. Or is there some other trend or pattern? You just want to describe what you see. Here I see a straight line. Here I see a curved pattern, right? Here I see no pattern at all. This looks totally random. This looks totally horizontal. These are considered no association. So you don't have to do a lot of really deep analysis with this stuff. It's all descriptive. We're going to have our calculators do the work for us when it comes to describing the data, okay? I mean, when it comes to like the deep connections between things, you just have to describe what you see. Now, there are positive or negative associations. And if the trend is generally upward from left to right, that's called a positive association. The way you remember it is always move left to right. And if the points go up, it's positive. Over here, we have a negative association. If we move from left to right, if the points start going down, that's a negative association. So look at what we have so far. We have linear or nonlinear, and possibly no association at all, or very weak association. We're going to see that here in a second. And now we have positive or negative. So lots of ways to describe these things. So this is how you describe strong versus weak association. The strength of the linear association is determined by how closely the points are clustered together along the trend line. Here, our trend line is negative, right? And it's not super duper strong linear, like it doesn't look like a straight line, but it's generally linear. It's just very weak. So I don't see curvature. It doesn't look totally random. There's some pattern, it's just a very weak pattern. So that's called a weak association. Here is another negative association. You can see that it is generally more tightly clustered along that, that line. Just imagine a line here. And so that is a stronger association. So, but these are both linear because there's no big curves, right? So if you see big curves, there's really nothing we can do in a class like this. We just don't get into the curve stuff too much. And of course, we always look for outliers. So outliers are any points that are just away from the linear trend. So outliers in scatterplots are different than outliers in our other graphs. When we had an outlier in a box plot, there was no direction for a box plot. There's no such thing as a direction, right? The points are either, to the right or to the left. Here, we're on an XY axis, so the trend is only going to fit one of the directions, right? The data can only have one trend. Any points away from that main trend Like if it's this far away, it's definitely an outlier. But anything that looks even a little bit away from the trend could be an outlier. We're going to learn more about outliers in the next section. But for now, you're just looking for points that jump out as being very far away from the trend. So the way we describe our initial scatter plot, the one we saw at the beginning, for our honeybees, linear, certainly, positive because it goes up as you move to the right, strong because the points are tightly clustered along the trend, and no outliers. Right? Outliers would be away from the trend. None of the points here are away from the trend. So that's all you really have to be able to do, is just describe what you see. So here's a brand new data set. We're going to use this one a bunch in this section and the next section. Describe the association, which shows the price in dollars and size in square feet of 100 houses for sale in Florida. Are there any outliers? So let's see what we have here. Here's the size of the house in square feet. Here's the price. So we know that bigger houses cost more money. Everybody knows that. And that's shown in the trend. So it's definitely a positive association, right? And it looks fairly linear. I don't see any big curves, and it doesn't look random, and it's not horizontal. So this is linear and positive. How strong is this association? Does it look more like more points are along the trend, or more points are randomly scattered? If it looks like more points are close to the trend, then that's a strong association. And if you're not sure, just go back to an earlier slide, strong versus weak. This one's weak because it looks like more points are randomly scattered. There's a few points on the trend, but not many. Here, almost all the points are on the trend, so it's strong. So for this one, more points are clustered along the trend. They don't have to be real close. They just have to be, relatively close compared to some of the other points. So this is a strong association. And last question, right? So we have linear, positive, strong. Last question, outliers. Well, outliers are tough because we don't know exactly where the trend line is. Is the trend line more up here? Is it more down here? It's hard to say. Maybe this one might be an outlier. If the trend line is real high, then this one could be an outlier, but so could this one. Right? And this one could be an outlier as well. So outliers are very hard to discover. We're going to use technology to do all this stuff. Here's a different data set. This scatter plot shows the maximum weight bench press in pounds and body fat percentage for 64 female college athletes. So this data set could be used to maybe you're studying weight training or physical therapy, and you want to know, can you use somebody's body fat to predict their maximum bench press? Well, does it look linear? Can you see a trend, a straight line trend in the data? Not really. Well, here's the thing. Once it looks more random than it does look like a trend, then a lot of the other questions we have don't have any meaning. So if there's no trend, then we can't say that it's positive or negative. If there's no trend and it looks random like this one, or nearly random, then it's a weak association, because a strong association would be clustered along the trend. Because there's no trend, can't be strong, so it needs to be weak. And the last question, outliers. If there's no trend, there's no outliers. So we can't even really discuss outliers. And that's it. That's all you have to do, is just try to describe the associations. Now we're going to look at a single number that does the describing for us, and it's called the correlation. So the correlation is a very technical statistics term. It is a number between -1 and 1 that measures the strength and direction of a linear association between two quantitative variables. So before we go any farther, I just want to point out something. A lot of students mix up the idea of correlation and association. Association just means there's any sort of connection between the variables. Correlation is a special kind of association that is linear, and we can describe the strength with the number that we're going to get. So we're going to have our calculator compute the correlation, and then we'll look at the graph, and the correlation number will describe the association. So the correlation between two quantitative variables from a sample is denoted R. Most of what we're going to be doing is on the graphing calculator, so we're going to use R most of the time. But populations do have correlations, and we denote that with rho, and that's pronounced R-O-W, like row your boat. So we're going to be dealing with R mostly because we're going to be inputting data into the calculator, usually from a sample, but populations do have correlations, right? So just as a quick example, if we go back and look at this is a sample of 100 houses for sale in Florida. So the correlation of this sample is going to be denoted R. But there is some correlation between price and size for all houses in Florida, right? Bigger houses do cost more money. There is a correlation in the population. So if we were talking about a population, we would describe it with rho. But when we type the numbers into our calculator or into StatKey, we use R. So just remember that populations have these numbers, even if we don't know what they are. All right, so here are some properties of R. So if you type numbers into your calculator or StatKey, your R value is always going to be a number between -1 and 1, but it's allowed to be -1 or 1. The sign of R indicates the direction of association. So if R is positive, the association is positive. If R is negative, the association is negative. Values of R close to plus or minus 1 show a strong linear relationship. So it can be strong and positive or strong and negative. Values of R close to 0 show a weak linear relationship or none at all. We've seen how that can work. Curvature can be considered nonlinear, so that could give us an R close to 0. Completely random looking scatter plot, R could be close to 0. Or actually a horizontal line, R could be close to 0. So an R close to 0, we don't know what the graph looks like. We just know it's not strongly positive or strongly negative. The correlation is symmetric. Switching the data columns for X and Y will not change R. On the homework, if you accidentally switch X and Y, you're going to get the right answer for R. I'm not saying you should switch those, because there's other things in the next section that you will get a different answer. So make sure you're paying attention to which one is X and which one is Y. And last bullet, the population correlation rho also has all the properties listed above. All right. So let's talk about how to use technology for a TI-84. So I'm just going to read through this, and then I'm going to go ahead and do the next example. So if you have the PowerPoints printed out, you can look ahead when I'm doing it. I'm just going to flip back and forth while I enter the data. So everybody in the class needs to do this first step only once the whole semester. There's another, in the next section, we do something similar to this. I'm not going to go over it in the next section. Just do it once, even though it's in the notes, just in case you forgot to do it. Maybe for some reason you're watching the next video before this one. You know, maybe you saw 2.6 and now you're coming back to this one. So I put it in there twice, but you only need to do it once. You don't have to do this every time, just once. So what we're going to do is you go to second, catalog, which is above 0. And then you want to turn on your diagnostics, and it's way down here. So you got to click this a whole bunch of times. It's no fun. And you just want to turn diagnostic on. So hit enter once, hit it twice. As soon as you do that, you never have to do that ever again. Now, if you happen to, let's say your batteries die and you need to change your batteries, you might need to go through and do it again, okay? But for each set of batteries, you only need to do that once. That will turn on the correlation. All right, now we're gonna put the data in. So you go to Stat, we're gonna edit, and then we're just gonna hit enter. So it's edit, right? So it's the same thing we did before. Notice I have some data here. So I'm gonna clear the data, same way I did before. I'm gonna go up to L1 and just hit clear, and then hit enter. Do not delete this. It happens every semester, somebody deletes something. Please always clear, never delete when you're in these lists. All right, so yeah, we did that. And yeah, if you have data in L2, just do the same thing. Just go to L2, clear, hit enter, it'll clear it. Now we type the values of the X data into L1 and the Y into L2. So you don't enter this in rows, you enter it in columns, like you're using Excel or something. So let's go ahead and put the data in. So I'm gonna go to the next slide. The data's here. So I'm gonna put in our honeybee waggle dance data, right? So it's 0.4. So we just put it in columns, right? 0.45, 0.95, 0.32, 3.1, and 4. You have to hit enter after each one, and then go through and make sure you typed them in right. So just scroll around. So it should look like this when you're done. You don't have to type all the extra zeros. The calculator knows what's going on. 200. So I'm going to go and just put them in. And you want to try this at home. So when I get to the end here, pause it and make sure you're getting what I'm getting. This stuff will be on the homework a bunch of times, and it will be on an exam. And on an exam, you have to know how to do this. You have to use your graphing calculator, and you have to be able to do this on an exam. And it's totally with technology. Doing this by hand would be one of the most horrible calculations you've ever done in your life. If you're interested, go ahead and Google it. Google formula for correlation by hand, and let me know when you can't take any more. All right, so we're not even going into the formula for the correlation. It's in the book, but I don't want to scare anybody. So here, look at what we have here. We've put our data in. So, here's our first honeybee scout all the way down. Here's our last one. Now, what you do is you go to Stat Calc. So Stat, we go over to Calc. Now, we did 1 and 2 variable stats. That's something we could do. But we're going to go down to number 8, which is linreg A plus BX. Okay? Before we go any farther, I want to point out something. There is another linreg here, number 4, which is AX plus B. You cannot use this. In this section, you will get the same answer for the correlation. In the next section, 2.6, you're going to get the wrong answer if you do that. And you won't know why you're getting the wrong answer because we're using technology. Use number 8, enter. These should all be set up correctly. If for some reason you deleted one of your columns, you can go through and rename these using the lists that I showed you before. I hope that doesn't happen, but you can still do it. Just don't delete any columns. So just keep hitting enter. All right, and you're going to get all of this stuff. So the only thing we care about here is, let me try it again. Hit the wrong button. So, here we go. The only thing we care about here is this R. We do not use R squared in this class. Don't ever use that for anything. Some of you may end up in another class later that uses it. Great, we don't use it. And A and B we will use, just not right now. Okay, so we're using R. So you should have gotten 0.994. So the scatter plot has a correlation of 0.994, which is strong and positive. So R tells us if the data are linear, then it is a strong positive correlation. If for some reason the data has a big curve in it, then R is meaningless. Okay, it still might be positive, but the strength of the association is meaningless. So just watch out for that, okay? It has to be more or less linear or we can't do anything. So here is an example about how to estimate R. So we're not using the calculator for anything, we're just using the graphs. Let me point out something else that happens. Every semester, so something like this might be on a test. Every semester I have people that try to type these data points into their calculator and compute it. Please don't do that. Use the rules of what R tells us. Remember, if you see a straight line trend, determine, does it look like the points are close to the line? That means R is close to 1 or close to -1. If it looks random or it's horizontal, R is close to 0. So what do you think the correlation is here? Well, do you see a straight line trend? Yes. Is it positive or negative? Negative. That means it's going to be close to -1. Does it look like this is a perfect straight line? It does. So this correlation is exactly -1. So you can't get a better correlation than this. What about B here? Does it look like a straight line trend? No. That means R is going to be close to 0. Does it look completely random? Yes. That means R is exactly 0. So here R is -1, here it is 0. When you guys are doing the homework for this, or maybe even on an exam, these are either going to be multiple choice, matching, or write in a number that's close. You don't have to estimate R, to 3 decimal places or something. You just got to be close. So if I said, which of these graphs has an R of -1, it's this one, because it's the only one with a straight negative trend. Here we have a straight line trend, and it's positive, but it's not a perfect positive trend, right? There's some clustering, but it's still a little bit random looking. So R is going to be close to +1, but not exactly +1. So why don't you guys try to estimate that? The solutions for all these are at the end of the slides, just because I want you to be able to go back and practice these skills. So I put most of my solutions are in line, but these I put all at the end, just so you can go back and practice over and over again. So here's our Florida house price data set. What do you think this correlation is? So, is it strong? Yes. Is it positive? Yes. Is it perfectly straight line? No. Maybe a couple of outliers. So again, it's going to be close to 1, definitely bigger than 0.5. A correlation of about 1/2 is pretty fuzzy. This one looks like a pretty strong trend though. Okay, so it turns out this correlation is 0.761. Again, if this is a test question, you just have to be close, or it'll be multiple choice. So here we have a correlation of 0.761, which is a strong positive correlation, right? So think about it, right? A correlation of 1 would be perfectly straight. But here we maybe have a few outliers, and it's a little fuzzy, so it's 0.761, but it's still a strong positive correlation between the size of the houses in the sample and their prices. So it's just a descriptive term. It just tells you how strong the association is, the linear association. And using inferential methods from later chapters, it can be shown that there is a significant association between the variables and the population as well. We're going to do that later, starting at around chapter 3. So, strong, positive, linear. And it turns out that this is a significant association. Does this mean that the size of the house causes the price to change? So there was a question that came up on a discussion board in one of my classes about cause and effect relationships and confounding variables. Well, there's lots of reasons why a house could be bigger or smaller, and lots of reasons why a house could cost more or cost less. The size of the house is one of many things that can cause the price of a house to change. But that's not why the answer to this question is no. The reason is because of this, because of one of our correlation cautions. A strong positive or negative correlation does not necessarily imply a cause and effect relationship between the two variables. Only a randomized experiment can show causation. This scatter plot came from a study that was clearly not an experiment. If you're trying to find out things about houses for sale, that's an observational study. You can't assign houses to be different sizes. You're not going to hire construction workers to build, additions on houses and knock down parts of a house to change their size. It's an observational study. Anytime you have an observational study, you have confounding variables. And whenever you have confounding variables, you can't have a cause and effect relationship. So I put a little XKCD cartoon in here. This really says everything about correlation, right? I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. So there's a lesson there. Just because you have a conclusion doesn't mean it's a cause and effect conclusion, right? You need a randomized experiment. Now we have other cause and effect, we have other cautions, other correlation cautions. Second correlation caution is low correlation does not mean no association. This is the hardest one to understand in general. Because you might think a correlation near zero means that there's no association, but that's not true. I've seen studies where there is an association and the correlation is like really, really close to zero. So the correlation doesn't mean no association. Correlation measures only the strength of the linear relationship. In practice, if the correlation is very close to zero, we will usually conclude that the linear association does not exist between the variables. So there's no perfect guideline to go on. Usually, though, something close to zero would be, think of it like percentage points, right? It's not the same thing, but as a ballpark, just think about it. Zero would be okay. If your correlation is 0.01 or negative 0.01, no association. It might exist in the real world, but we don't study it to that extent in this class. So for our purposes, if your correlation is 0.05, you can also say no association. So really, as long as it's within, let's say, 10 percentage points on either side, if you're thinking of it as a percent, right? If that helps you remember. But there's no perfect guideline for this stuff. There's just, you have to compare it to some other things. And we'll show you that later. But for now, numbers close to zero, no association or very small association. And then the second bullet here tells us about something else. We need to look at the scatter plot to see if there's a curved pattern that may indicate nonlinear association. A curved pattern could indicate a positive or negative association, even though the correlation cannot be applied to curved data. So you can have a positive association that's curved. It'll still be a positive association. But the correlation, the number for the correlation doesn't have any meaning. So I know that that's kind of strange based on what I've been telling you, but it still should make sense, right? There's lots of data in the real world that is associated, but it's associated in a curved manner still could be positive or negative. We're actually going to see one of those in the next section. You'll see an example of a curved data set that has an association, but the correlation doesn't have any meaning. Last correlation, caution. Correlation is not resistant to outliers. Always plot your data. So outliers can really change a correlation. So here, this is the data. This is the scatter plot we saw earlier. This shows the worldwide earnings in millions of dollars and the opening weekend earnings in millions of dollars for a sample of 100 movies. These are Hollywood movies that came out from 2007 to 2013. One movie is a severe outlier with its response variable value far above the trend, right? So we saw this before. So this is just a random sample of movies that came out in this time period. And here's their opening weekend, and here's their overall gross earnings. So most of the movies cluster around this trend line where, if the trend line is like right here, right? So if a movie makes $40 million on its opening weekend, it's going to make about, $300 million or something, or $200 million, right? That's the trend. And so you can see the trend moving up. This movie made $80 million on its opening weekend and then made $2.8 billion in this time period. So that's an outlier. So what happens if we take out the outlier? I'm going to remove it to show you what happens to the correlation. This is still a strong correlation here, right? 0.731 is a strong positive linear correlation. It looks pretty linear other than the outlier. I took out the outlier and the correlation jumped up from 0.731 to 0.920. So you can see that the outlier is affecting the correlation severely. But this brings up another question. Can we remove outliers if our correlation is low? So if you're trying to learn something about Hollywood movies, maybe you're studying Hollywood movies in some sort of class, that outlier is messing up the conclusions you can draw, right? The correlation is lower, so your conclusions won't be as concrete. Should we always remove outliers? Well, it turns out that outliers have a large effect on the correlation, but they should only be removed if they are data input errors or they belong to a sample from a different population. That particular movie that was here and then got removed, there's nothing special about that movie. People went back and saw it over and over and over again. And that's why its opening weekend wasn't very huge. But, it was still a blockbuster, right? It was still fourth biggest in the sample. But you can see that people just went back and kept watching that movie over and over again. So there's nothing special about the movie. It's not a Star Wars movie or something where it's going to make $1 billion no matter what. So I only remove the outlier to show you what happens to the correlation. You're really not allowed to remove outliers for any reason. Now, if it's a data input error, if somebody typed it in wrong, so maybe noticing an outlier would cause you to do some further research. Or if you notice that this movie doesn't belong there anyway, maybe that movie came from outside of the time frame specified, so that movie doesn't belong there, and you can take it out. But it turns out that particular movie is not special and needs to be left in if you're trying to learn something from that study. And last thing here, correlation is a valid measure only if the relationship between the variables is linear. If the graph shows obvious curvature, the correlation is meaningless. So I talked about that before, but there it is. You got to plot the data to look for outliers and curvature. So here's the solutions. We went over all this stuff, obviously. And here's the important information from the section. And of course, if you need extra practice, here's some extra practice. One thing I want to point out about these optional book exercises, one of these is your data from Lab 1, this one right here. So definitely want to at least take a look at that one because some of the answers to that are the same answers from the lab. So lots to work on here. Oh, and then I put an even problem in here. The answer's not in the bag, but 192 and 193 go together. They're complementary problems, and they're homework problems. And so it's nice to see this one. You can see the answer. This one you can't, but you can kind of see what's going on. It's about reading a trend from a scatter plot. It's a pretty interesting example. All right, well, that's it for today. If you guys have questions, email me or post on the discussion forum or ask during class. And I will see you next video. Until then, study hard. Bye-bye now.